Thinking Aloud. Conversations on the leading edge of knowledge and discovery with psychologist Jeffrey Mishlove.
Hello and welcome. I'm Jeffrey Mishlove. Today we are going to look at consciousness theory, by which I mean Stuart Hameroff and Roger Penrose's Orch OR theory and its enemies. With me is Stuart Hameroff, who is the director of the Center for Consciousness Studies at the University of Arizona. He is a professor of anesthesiology at the Banner University Medical Center at the University of Arizona, is also a professor of psychology, and one of the pioneers in the field of consciousness theory. In fact, probably more than any other single individual has been spearheading the scientific study of consciousness. Welcome, Stuart.
Thank you, Jeffrey.
It's a pleasure to be with you once again. The intriguing thing about your theory is that it has attracted so much opposition, and for decade after decade after decade since I first met you, you have been steadfast in refuting all of those arguments. And yet, while your theory, as I understand it, really remains the only complete theory of consciousness, it's still, I think, fair to say, a minority viewpoint within academia.
Yes, definitely. I think we're gaining ground. I think it's becoming more accepted. People are at least paying attention to it. We're getting a lot more notoriety. But I thank you for saying that. I have to agree it's the only complete theory in that with Roger's work and my work, we cover philosophy, physics, general relativity, biology, neurobiology, pharmacology, anesthesia. We can explain how anesthesia works, for example, to selectively erase consciousness. And yes, it's attracted a lot of criticism over the years. People could hardly contain themselves from criticizing us gleefully initially. But it's better to be criticized than ignored. And after 20 years of criticism, we're still here. In fact, I think we're gaining ground, and evidence in the last 10 years in particular has strengthened our argument considerably.
Well, it's a lot easier to criticize a theory than to build a theory.
Yeah. And the other theories, there are a lot of other theories, but I think I would agree with what you're implying, that they're partial. Mm-hmm. They might deal with, just a complexity argument, or just panpsychism, or emergence, or this or that, or a particular brain area, but they don't really give the whole picture and to explain all the details and facts and what we believe about consciousness.
And particularly address the hard problem, which we discussed in a previous interview.
Yes, the big enchilada, the hard problem.
Well, what would you say is the main academic thrust against the Orch OR theory at this point?
Well, what we proposed and still proposes that you have to go to a deeper level inside neurons. Most people view the brain as a collection of neurons acting as fundamental units, but every neuron is incredibly complicated, although complexity per se isn't the answer. If you think of a single-cell organism like a paramecium, it's very clever. It doesn't have any synapses, so it's not just a network effect. And a lot of people are talking about multi-level multi-scalar hierarchical looks at the brain, but they start at the level of neuron and go up. So a neuron is the fundamental unit. And they go from maybe hundreds of hertz to hertz in terms of frequencies. So 100 per second down to 1 per second, EEG, for example. But if you go inside the neuron, we know that the microtubules have dynamics that go, if you're going downward in size and faster in scale, kilohertz, megahertz, 1,000,000 per second, gigahertz, 1 billion per second, and terahertz, 1 trillion per second, down to the level of microtubules and quantum oscillations of the pi resonance groups. So we see a multiscalar hierarchy extending downward deeper inside neurons. And it's kind of interesting that in AI, the biggest advance in the last 10 years has been deep learning, where they actually add a deeper level into their networks in between their nodes, and they get all these interesting effects. So
now
it's
we're talking
like
artificial intelligence.
artificial intelligence. They've gone to this route without even realizing that if you extend that to the brain, what you're saying is you have to look inside neurons, which is what we did, and that's where we get the quantum effects.
And yet, if I understand it correctly, the AI people who feel that once computers are sufficiently complex, they pass this singularity, then they will become consciousness. They're one of your strongest opponents.
Yeah, they don't like us. Because basically the singularity idea, and it actually goes back to Hans Moravec and many other people earlier, singularity being Kurzweil, but they take, let's say the brain is 100 billion neurons switching at about 1,000 per second with 100 synapses. That's 10 to the 11th times 10 to the 3 times 10 to the 2 gives about 10 to the 16th operations per second. And they say, well, when we have a computer that can do 10 to the 16th operations per second, we'll have brain equivalents, we'll have consciousness. Give us another couple billion and we'll build it for you. And
that's likely to happen, I'm guessing, in the next 10, 20 years.
I think it might already be there, but they're not talking about it because they should have had consciousness by now. So they keep moving the goalpost.
Yeah.
So I had been studying microtubule information processing inside neurons, or all cells, for about 20 years, in the 70s and 80s.
Yeah.
And I was going around a neural net and AI meetings saying, no, you guys are naive. You have to, it's because if you look at the level of microtubules, you have about 1 billion tubulin subunits, proteins, per neuron, switching at about 10 megahertz.
Yeah.
So that gives you 10 to the 16th operations per second for every neuron. So there's enough information processing in one neuron to match what you're saying you need for the whole brain.
Yeah.
So you'd have to multiply that to give something like 10 to the 27th operations per second. So I was saying their goalpost is way further down. So they didn't like that. They said, go away, you bother me. You know.
Sure, but I think it's fair to assume that within 100 years they'll reach that goalpost.
Right. That's quite true. But computation per se is not the answer. And one day, in fact, somebody said to me, okay, wise guy, let's say you're right, and there's all this information process. How would that explain consciousness? He basically threw the hard problem at me before the term had been coined.
Because you don't need consciousness for computation.
No. And but they assume computation gives you consciousness. That's the fallacy, I think.
Yeah.
So this person, I can't remember who it is, but I remain indebted to him, said, he kind of stumped me, and I said, I don't know that, how love, joy, feelings, emotion, consciousness, how do you get that from computation, even at the microtubule level? And fortunately, he said, why don't you read this book by Roger Penrose, The Emperor's New Mind, which I did. And Roger had a solution, the subjective reduction, but he didn't have a quantum computer that could implement it. So I thought
your specialty.
Right. So I thought microtubules could be his quantum computer, and objective reduction could be the mechanism I was looking for.
I didn't mention, by way of introducing you, that your first book, Ultimate Computing, is all about that quantum, tiny computing in the brain.
Right. I hadn't gotten the quantum bug, and I think in retrospect, although it was basically an ode to microtubules because I was fascinated with how interesting and capable they were, but it didn't include the quantum aspect, and so I didn't really explain consciousness. It did explain a lot about microtubules, though.
I know you have consciousness in the subtitle, but at that point in your development, you hadn't really come to grips with the hard problem.
Correct. So it was a little bit of a promissory note in that regard. But in retrospect, I think it's in the microtubules, but in a different way than I realized.
Somewhere along the way, you saw the light.
Yeah.
So now...
My enemies, our enemies. So the first big thing was if you want to build a quantum computer in a laboratory, it's plagued by heat, thermal noise, thermal vibration.
Right.
It's called decoherence. It destroys the quantum effect. So
which is another big attack against your theory.
Yeah, this is the main attack. The
Tegmark, as I recall.
Max Tegmark, yeah. So and others and they build the quantum computers at absolute zero temperature to avoid these decoherence. So people would say, well, how can you expect a delicate quantum operations at 37.6 degrees centigrade as we have in the brain? And Tegmark wrote a paper in 2000 where he calculated the decoherence time of a microtubule, but he didn't really use our model. He used his own model. Basically, he had a soliton propagating along a microtubule separated by 24 nanometers. 3 tubulin lengths, and he calculated the decoherence time as, according to that, as 10 to the minus 13 seconds. Way, way, way too fast to be of any use. We were thinking that we needed to avoid decoherence for up like 25 milliseconds for EEG. For example, we're trying to relate it to EEG. Turned out we don't need to do that, but he made a couple big mistakes. In our approach, the superposition separation of the solitons, 24 nanometers, was 7 orders of magnitude off of what we claim, where the superposition is to the level of the nuclei in the carbon atom. So that's Fermi length, 10 to the minus 15th. So that was 7 orders of magnitude. He made 2 other mistakes. So I showed the paper to Roger. We were at the RAND Corporation in Washington, I remember. He said, well, let me look at it overnight. And so in the morning at breakfast, I said, what'd you think? He said, according to that, quantum mechanics is impossible. It's not even, I said, should we respond to it? And he goes, why? It's ridiculous. So he's more polite publicly, but I can tell you he said something like that. But I got 2 of my physics colleagues, Scott Hagen and Jack Tuszynski, and we took Tegmark's same formula that he developed. He did us a favor of developing a formula for decoherence that we could use for microtubules, but changed the superposition separation distance. That gave us 7 orders of magnitude and a couple of others. So we got it down to 10 to the minus 4th seconds. So which was close, but not quite there yet. It turned out later that was plenty because in our recent work, Roger came up with the idea of, since we now know that there are these quantum vibrations in microtubules. I'm skipping ahead a little bit, but Anirban Bandyapati showed quantum resonances in microtubules from terahertz, gigahertz, megahertz, and down to kilohertz.
This is crucial to your theory, isn't it?
Exactly. And 10 kilohertz is 0.1 milliseconds, which is what we predicted. So that prediction was verified by Anirban's results.
Well, many of our viewers are not going to follow all the numbers and the mathematics, but I think the key here, if I understand it correctly, is that you've got these resonances going on throughout the brain at the neuronal level and at the subneuronal level, down to the microtubules and even below the microtubules to the
quantum level.
To the quantum level. And all of these levels...
And below that to space-time geometry, which is how you get the hard problem.
All of these levels have to be somehow orchestrated together in order to get what we know of as human subjective experience. Right.
In fact, orchestrated, which was the term we came up with to organize the objective reduction, is also metaphorically appropriate, because I think in some sense consciousness is more like music than it is a computation. You have this multiscalar vibrational hierarchy, and a lot of people agree with that, but they take it only down to the neuronal level, so they're just truncating it at a very high level. If you go down to this, you have from 10 to the 12th, you have 12 orders of magnitude. And Anirban showed these repeating resonance patterns, triplets of triplets at all these levels. And so I think it's more like music with resonances across scale.
Now, my best guess is that one of the reasons that so many academics are having trouble with your theory is exactly that. They don't relate to the metaphor of music and the orchestra. They're still thinking about a mechanism, a clock, or a computer.
Right. I think a computer is not the way to go. I mean, you could say, we compute, but a lot of things compute, depending on how you define it. So, systems generally interact and there's a result, so everything's a computation in some sense, but I think that misses the point. A multiscalar vibrational hierarchy going from higher all the way down to 10 to the 12th hertz and below that. And 10 to the 12th hertz is also where anesthesia works. And one of the, I think the essential way to test a theory is to see if it explains consciousness and the loss of consciousness with anesthesia. So I've studied anesthetic mechanisms for many, many years. I'm an anesthesiologist and have published a lot in this field. And most people would say that anesthesia works on membrane proteins, GABA receptors, acetylcholine receptors, serotonin, and a few others. And in fact, they do bind to them, but they don't all bind to all of them. And one will open the channel, one will close the channel. There's no unitary mechanism. And actually, the really advanced thinkers in this area have discarded that. And beginning about 10 years ago, 2 things. One is that they found quantum coherence in plant photosynthesis.
Mm-hmm.
So in sunlight. So the idea that you need absolute zero temperature is out the window now because plants do it. If a potato or rutabaga can figure out how to use quantum coherence, our brains can probably do it.
Yeah.
Is an argument. And so it's kind of a universal thing in biology.
Well, now let me ask you, that sounds like such a strong argument. Has it been persuasive?
No, because people, they don't want to go there. And one argument against it, I'll be my own critic here, is that in the FMO protein in plant photosynthesis, the quantum state goes just about a nanometer and is very short-lived.
Yeah.
Now, if you imagine taking that and making a linear chain or in a helix like a microtubule, it's going to be much, much longer. And you can get resonance, so you get much, much longer coherence time. And in fact, Anirban has shown that in his nanotechnology experiments.
Yeah.
So my colleagues Jack Jasinski and Travis, well, let me back up. A guy at the University of Pennsylvania, beginning about 10 years ago, Rod Eckenhoff, showed that with systematic experiments, showed that anesthetics bind to 70 different proteins in neurons. Half in the membrane and half in the cytoplasm, including tubulin. He then did genomic and proteomic analysis of which genes were turned on, and which gives you an idea of the function of which of those are inhibiting the functions. And it turned out that tubulin, microtubules, were the answer, and they seem to mediate the functional aspect of there would take away the functional aspect that's taken away under anesthesia. And they also did optogenetic studies that point to microtubules. So that's just beginning to come out, and Jack and Travis and I have done work in computer simulation of these terahertz vibrations, showing that anesthesia, all the anesthetics inhibit the terahertz oscillation proportional to their potency. And we have a paper that we're revising for a major journal right now that will make that argument quite strongly. So we're gonna come out and say that anesthesia acts by dampening the fastest, smallest level of this hierarchy, and that dampens the whole cascade. And that's
which I gather when you're talking about vibrations in the terahertz range going on in the human brain, that is so far outside the normal training of people in neurophysiology that they have an awful hard time relating to it.
And they could also say with some validity that, well, that's way too fast for anything that we know about. The brain acts milliseconds and whatnot. But with this cascade, terahertz, gigahertz, megahertz, kilohertz, then hertz, it's the bottom level of this hierarchy cascade. So it's kind of setting the beat in the orchestra, so to speak. And so when you inhibit that, everything else slows down or goes away.
The other thing that I imagine has caused you some problems in academia is the fact that you're very open about being open about parapsychology, psychic phenomenon, for which there's an enormous empirical database, but which is also a taboo subject. And you have kind of opened the Pandora's box, and I suspect it causes many conventional people just to think that you've gone off your rocker.
They cringe, some of them. But if consciousness is a quantum effect, there's non-locality, there's entanglement. We have all this evidence from parapsychology with non-locality, backward time effects, near-death and out-of-body experiences. And I think if consciousness is truly a quantum effect, which I believe it looks like it is, then these things are possible. So I just say they're possible. I don't, get into trying to prove or disprove this bit of evidence versus that bit of evidence. I'll leave that to the parapsychologist. But I think, until we know how consciousness occurs in the brain, we cannot exclude it occurring out of the brain.
Well, you're going one step further. You're saying not only is it possible if it's real, of course it's possible if it's real, but you're saying it would be not inconsistent with your theory.
Exactly. And Roger's a little reluctant to go there because, but he has said things like that, and but he's much more guarded about it than I am.
Well, there's a sociological effect here. That for whatever reason, historically speaking, I know it very personally because I have a doctoral degree in parapsychology.
From Berkeley.
I got it 30 years ago from Berkeley. It's the only one ever awarded in the world. Ever.
Congratulations.
Well, thanks, but I'm kind of lonely in a way. I mean, one of the main reasons I do these interviews is because I know the day will come when when that will change, and the academics are going to finally open up their eyes and say, here's a mountain of empirical evidence we should have been paying attention to all along.
Right. And one of the big things in that is this backward time effect that we've talked about. And I've looked at this very carefully over the years. Ben Libet, who was at the first conference, you probably met him there. People talk about Libet's experiments, and they always talk about moving the finger and the idea that there's this readiness potential, and they use that to argue against free will, actually.
Yes.
And I think that's a mistake, and Aaron Sugar and others have looked at this and reanalyzed that. But the experiments they ignore are even more interesting ones, where he went to the operating room, he had a neurosurgery colleague, and they did craniotomies under local. So they had the patient's brain exposed while they were awake. You can do it under local anesthesia, and once you're in the brain, it doesn't hurt. And Libet was able to, for example, stimulate the brain directly for this pinky, for example, and ask them, and stimulate the pinky, in both cases, ask them when they felt it, with a very sophisticated, and you would expect that if you stimulate the brain, you'd feel it immediately. If you stimulate it here, there'd be a delay.
Yeah. So that the neural signal can travel to the brain.
Yeah, but that's only 30 milliseconds, and that is real. But what he found was stimulating the brain directly for, let's say, the pinky area. You'd feel in the pinky, but only after a half a second, which is a pretty long time.
Yeah.
And then he did some clever things where he stimulated the thalamus. And if you stimulate here, you get what's called an evoked potential, a big spike at 30 milliseconds. And that's when you feel the prick or the experience. He found that if he stimulated in such a way where he got the spike, he got the evoked potential, but then didn't have this ongoing activity for half a second, there was no conscious perception. So the brain apparently needed to know that there would be this ongoing activity, and he concluded that meant that at the time of what he called neuronal adequacy, after 500 milliseconds, the information was referred backward in time to the evoked potential, so we feel it at the evoked potential. So this retrocausal, I'm not sure it's causal, retrocorrelation, this backward time effect has been seen in things like the pre-sentiment experiments, where you get a galvanic skin or impedance change from looking at images even before the images appear.
This is parapsychology research.
Exactly. Radin and Bierman and so forth. Well, and then Daryl Bem's work.
Yes.
And, the problem is if it gets labeled parapsychology, it gives people license to ignore it. Oh, that's just parapsychology. So I just think of it as psychology and physiology.
Sure.
And the backward time effects, and then Daryl Bem's series of experiments, which he presented at Tucson a few years ago, which was in a mainstream psychology, but still manages to get ignored now. Despite people don't want to deal with it because but again, until you can explain consciousness classically, then there's no reason to exclude these because they can be explained by quantum effects.
But so what you're saying is that a very important part of your theory is the idea of retrocausal correlations going on in the brain.
I think you need that for the possibility of free will. For example, if you and I are talking and you say something and I answer back immediately, if you were to record my brain for the activity that correlated with what you said, I will have responded to you before that activity occurs. Now, people in neuroscience recognize this and take that to mean that I'm acting non-consciously and subsequently have this illusion that I'm acting consciously. That feeds into the consciousness is illusion idea. But where's the activity for the unconscious response? They don't talk about that. But if you have this backward time effect, it means that my processing of what you said goes backwards in time. So when I respond immediately, I'm actually doing it consciously, but I need information from the near future. And
it gives us the ability to anticipate things.
True. That's another thing. I might be picking up on what you're going to say. But even ignoring that, just what's happening in my head to respond, or your head when you respond to me, seems to require backward time effects.
Well, there is a sense, like here we are having a back and forth conversation. One might say we have the words, we have the neural activity, but there might be something going on even at a telepathic level between us.
Sure, there could be. Not only between us, from who knows where else.
Our viewers.
Who haven't seen this yet, but it doesn't matter.
Yeah. No, there's a sense in which they are with us now at a future time.
Could be.
Okay, I hope I'm not getting too far ahead.
It's hard to rule out anything. Because the quantum stuff is so weird. But, I just stick to the few hundred milliseconds from the lipid experiments. And I think you need that. I wrote a paper called How Quantum Brain Biology Can Rescue Conscious Free Will. Because neuroscientists and philosophers mostly have given up on free will. And one of the reasons is this phenomenon that the brain activity comes too late. So Daniel Dennett, for example, would say, no, we act non-consciously, and we have this conscious illusion after the fact. And there's no such thing as consciousness. It's just what we remember. But, of course, memory is a whole other mystery.
Yeah, how can you have memory but not consciousness?
Right, especially conscious recall of memory.
Yeah, and the idea that there is no such thing as free will, it might make sense in terms of Newtonian science, but it certainly contradicts everything in our legal system and our literary traditions and our poetic traditions, the whole field of creativity.
Right, which is could be non-computable effects, but there are other issues like determinism. So even if you get around this backward time effects, was I always going to do that? Because it depends on whether you look at the universe as a block universe where we're just moving through things that have already been created, or we're at the wavefront of something that's just being created. And I kind of favor the latter.
Well, the intriguing thing about in this time frame, in the 21st century, developing a complete theory of consciousness as you have done, is that so much of physics and philosophy and neurophysiology is up in the air.
Right. So what we're trying to do experimentally is to take the type of experiments that Anirban Bandyopadhyay has done, looking at these quantum resonances in microtubules, either isolated microtubules or inside neurons, and then bring in anesthesia. And anesthesia is fairly selective. If you put a patient to sleep under anesthesia, their brain is still quite active. And we take advantage of this in spine surgery, for example. We want to make sure signals are getting from the feet or the hands into the brain. So we're recording these signals while the patient is unconscious. So the brain is still functioning. Now, what we want to do is do these isolated resonance experiments in microtubules, put them in a chamber, and change from, say, air or oxygen to bring in a little anesthesia. See if the resonances dampen, and then you wash that away and see if they come back. It should be reversible as anesthesia is. So you do that with one gas anesthetic, let's say, and then you do it with another one that's twice as potent. The prediction would be that the second gas, you'd only need half as much because it's twice as potent. You'd only need half as much to inhibit the resonances. So we're planning on doing these experiments with Anirban's technology. And we hope to do it at what we're calling the Penrose Institute. A group of colleagues and I, James Tagg, Eric Very, Yvette Fuentes, and Roger are trying to set up a Penrose Institute somewhere in California, actually. So we're talking with funding people about it, and there's a lot of interest because a lot of these big funding groups are getting frustrated with the lack of progress in AI and conventional approaches towards really understanding consciousness, treating things like Alzheimer's disease. Everybody says, well, give us more money and we'll figure it out. But the basic problem in Alzheimer's, if I may digress for a moment, is you have the amyloid plaques outside the neuron, but then you have inside the neuron, the microtubules disassemble. The tau protein falls off. You lose the integrity of the microtubules, and the tau, which is like a traffic signal on the microtubules, and you lose memory and cognition. So we're trying to stimulate microtubule repolymerization with something, for example, ultrasound into the brain, which vibrates the microtubules. So we did a pilot study over the summer, which we gave last fall, I guess, gave some promising results, and we're trying to gear up to do a double-blind study. So it's a different approach. Rather than spending billions on a drug, and none of them have worked for Alzheimer's, we're trying to use this other approach with promising results, and we'll see.
Well, Stuart Hameroff, it's been a pleasure reviewing the progress that you've made over decades in developing this complete Orch OR theory of consciousness.
Thank you. I didn't get to some of my other critics, but maybe next time.
Well, we could go on for days, I suppose.
We're still kicking, though.
Thank you for being with me, Stuart.
Thank you, Jeffrey.
And thank you for being with us.